Hey everybody, it's Mr. Tima here, and I'll talk to you about forces, gravities, and Newton's second law of motion and friction and how all that's related. Now, this is kind of a bunch of topics thrown into one, but we'll work ourselves through it. And here we go. We got a lot of videos too, so not a lot of me talking, a lot of videos though to kind of prove points. So we'll be going jumping back and forth to the other screen here a lot. Okay, here we go. So Newton's second law. Who remembers what Newton's first law is? Newton's first law is inertia, or an object in motion will stay in motion, an object at rest will stay at rest unless acted on by an unbalanced or outside force. Okay, Newton's second law is actually this equation right here, which is the relationship of force, mass, and acceleration. This has to do with that broom ball lap we did. Okay, the idea of a larger mass will take a greater acceleration to equal the same amount of force, or a bigger force on a mass will cause a greater acceleration. Okay, and we'll talk about that as we do the lab and things like that. But the idea and how I remember this is probably not the most clean way to remember it, but it's like when you get in a fight with your mother, you say, "What the F, Ma?" Okay, so F, Ma is our equation here, okay? So force equals mass times acceleration. So again, this is the reason why if you kick a brick wall with a large mass, so you're applying a force to it, you're not really going to accelerate this wall, or you'd have to kick it extremely hard to accelerate this wall. When you kick a soccer ball with the same amount of force as you kick the wall, it has a low mass, so it accelerates very quickly, and we have fun. So ouch and fun, in case you didn't know. All right, we needed to start talking about this term called gravity. Gravity on Earth is measured as 9.81 meters per second squared. That means when we drop this ball, it's going to start accelerating. If you remember back to motion, okay, this is like a dot diagram. It's going to get faster and faster and faster, and eventually it will hit a constant velocity called terminal velocity, which we'll talk about later on. But acceleration due to gravity, it can be positive or negative. We tend to think of it as negative because we usually think about dropping something. We think of the earth as zero, and the ball is moving in the negative direction to it. All right. The cool thing is gravity is constantly pulling on everything. And if you take physics, you will start talking about this idea of projectile motion, but they actually fall at exactly the same rate. And if you look at this, if you look at every one of these guys, you'll see they line up perfectly. And some of you are like, what are you talking about? There's no way that can be possible. Well, I will do this demo in class, but if you're not in class, I'll show you this right here. The shoot and drop. Here we go. Let's look at this guy really quick. I fast forward it because it's quite the long thing here. So he's going to drop that ball and shoot this ball at exactly the same time. Boom. What's cool is they hit it exactly the same time, and I think they slow it down here. But if you actually listen, you'll see the secondary bounces are also at the exact same time. Of course, he doesn't do it again. He cleans up. But here you go. We'll try it one more time. Not only watch the first hit, but the second hit. So it has exactly the same amount of energy, and the reason it has the same amount of energy is because it's dropped from the same spot. I know that was a quick demo, or a quick little video, but there you go. Alrighty, back over here. Told you we'd be jumping back and forth a lot. Okay? So, Newton's second law. Force and motion are related. An object will have a greater acceleration if a greater force is applied to it. The mass of an object and the force applied to it affect acceleration. Newton's second law of motion connects these by that equation we talked of F equals ma. Ooh, it's a little hard to see. F equals ma, or A equals F divided by m if you solved for A. This is actually how Newton wrote it. Okay, this is actually how Newton wrote that. Any guesses why? Well, they actually could measure force and they could measure mass, but they couldn't measure acceleration. They had to calculate acceleration. They didn't have an accelerometer. This is actually how Newton and them helped starting to prove the actual number for the acceleration due to gravity. Okay, so here's just a quick little example. If you have a 1,000-kilogram car and you're accelerating it at 0.05 meters per second, then we'd have F equals ma. We know that the answer is 50. 1,000 times this is 50. Okay, So weight and mass. So we have our guy here standing on a scale on Earth, and the same guy goes to the moon and stands on a scale and it only reads 16.6 kilograms. Here it was 100, and here it's 16.6. Did the person change? Well, the answer is no. This person didn't lose a leg or lose arms or lose his body when he went to the moon, but he's only 1/6 of the mass. Because weight is the gravitational force exerted on an object. Your weight has to deal with your gravitational pull. Weight decreases an object and moves away from the earth because gravity decreases. That's why when you're in outer space, they say you're weightless. Okay? Weight results from a force. Mass is how much matter an object has. Okay, to clean that up, we're going to watch this little clip right here, our famous little Eureka videos. They're kind of corny, but they're really good.
Weight versus mass. If anybody ever asks you what a Newton is, yes, you could give them an apple, or a couple of golf balls for that matter, or a small flashlight battery, because all of these have a mass of about 100 grams. And when the Earth pulls them down with an acceleration of 10 meters per second, we say that the force of gravity acting on them is 1 Newton, or that the apple, the 2 golf balls, and the flashlight battery are all pulled down to Earth by a force of 1 Newton. How many newtons are pulling you down to Earth? Well, the simplest way to measure a force is to use a Newton spring scale. If we hang the apple on it, we see that the Earth is pulling the apple down with a force of 1 Newton. And if we hang you on the spring scale, we see that the Earth is pulling you down with a force of, just about 600 newtons. So now we know how much you weigh. What you weigh merely means what force of gravity is pulling you down to Earth. That's all weight is. The force of gravity. Remember how keen physicists are on Latin words? Well, gravity comes from gravitas, which is simply Latin for weight. But you thought you were weighed in kilograms, didn't you? That's true in everyday life, but not in physics, which has to be very careful about these things. In physics, kilograms measure your mass on a balance, but your weight is always measured in newtons on a spring scale. You'll have noticed by now that you can usually work out the number of newtons by multiplying the kilograms by 10. 100 grams, or 1/10 of a kilogram, is about the same as 1 newton, and 60 kilograms are about the same as 600 newtons. But if 1 kilogram is the equivalent of 10 newtons, why bother to make a distinction between a mass of 60 kilograms and a weight of 600 newtons if they both really come to the same thing? Oh. To find the answer to that, let's go to the moon. It doesn't feel as if you weigh so much here, does it? Let's see how many newtons are pulling you down on the moon. Only 100. Why is that? Because the moon is much smaller than the Earth, and therefore has much less mass. So its force of gravity is also much smaller, only 1/6 that of the Earth, in fact. This is why your weight on the moon is only 1/6 of your weight on Earth. What about your mass? On Earth, it was 60 kilograms. How much will it be on the moon? 60 kilograms. Exactly the same, of course. You don't get any smaller by going to the moon. You don't change. Only the force of gravity, and therefore your weight changes. That's the big difference between mass and weight. Wherever you go in the universe, your mass stays the same. Only your weight changes. So if you're not as slim as you'd like to be, don't eat so much. You should join the Mass Watchers Club, because you've got a mass problem. But if all you want to do is lose weight, go to the moon.
I don't know why that's so funny to me, but does anybody know what a cup on a plate is? What this thing's called? It's called a saucer. So this is like a flying saucer. All right. Well, anyway, I told you those are always corny, but they are kind of informative there. But there you go. There's the difference between weight and mass. Okay. All right. So now we also need to talk about this term called friction. Okay. Friction is a force that opposes the motion between two things that are touching. They're held together by things called microwells. These are areas of surfaces that are sticking together and is the source of all friction. I'll show you a picture of that here in a second. Friction between two surfaces that are moving past each other, but or that are not moving past each other, but are just kind of sitting there, like your hands on a table, or if you put your two hands together, that's called something called static friction. The next one's called sliding, which is when two things are sliding past each other. And then friction between something that is rolling across the other one is called rolling friction. So the three type that we need to know is static, sliding, and rolling friction. Here's a picture of a microweld. No matter how smooth you think a surface is, it has rough edges. Okay, and these little rough edges, like little pieces of Velcro, kind of stick to each other. Like here's a book sliding on the floor. Well, actually, what it looks like is the floor is very jagged, and the book's actually jagged. So they're kind of like grinding against each other. Now, at the microscopic level, it looks like they're grinding against each other. We might think something's perfectly smooth, but it's really not. All right, sliding friction. This would be a picture of sliding friction where two things are sliding past each other. And here's rolling. Now, what do you notice the difference between sliding and rolling? Well, hopefully you're noticing with sliding, you have a lot of surface area here. If you've ever had to push something that has like a big surface area, like a couch or something, it probably doesn't slide very easily. But a wheel slides, or we call it roll, it takes a lot less work because there's one point of contact. There's only one thing. You may actually have seen a box slide across, like at the grocery store, like the little rollers or something. It's very easy to allow something to roll over this. So you go to like UPS when they're shipping boxes, they push this little box and it slides forever because it's on rolling friction. There's very little contact. And since there's little contact, the amount of friction goes way down. All right. And that happens a lot in the Olympics. And we have some Olympics coming up here. So let's watch a little bit of the science of friction during the Olympics.
Curling has been in the Winter Olympics since 1998, but still seems a little strange to most of us. We had John Schuster, captain or skip of the U.S. curling team in Vancouver, explain this unusual sport for us, while scientists funded by the National Science Foundation explain how friction makes it all work. Curling, perhaps the most unusual sport in the Winter Olympics. A huge rock is thrust down a long sheet of ice. Two players sweep a path in front of it, guiding it to the center of the target, called the house. At the end of play, the team with the most points, the most rocks closer to the center, wins. Olympic bronze medal winner John Schuster is a lifelong curler.
My family is big into curling. I remember throwing, a rock at the curling club when I was, probably 6 or 8 years old.
Getting the curling stone from the start to the house is all physics, starting with a push-off against what's called the hack.
What you're able to do off of here is to position your foot to allow yourself to accelerate out of the hack with a curling rock. You can push out of this hack with a very high amount of force, and you know that it's going to transfer into the curling rock.
Then the sweepers move in.
This is like a synthetic material that has just a little bit of abrasiveness. Curling terminology as far as sweeping goes, it's anything that you could consider versions of yes. But usually it's hurry and hard. You want them to push harder.
To help the stone go farther and straighter.
Back in the old days, people used to think when you swept in front of a rock, you cleared out snow and frost, and that allowed the rock to go further. Well, after we got the snow and frost elements removed when we moved indoors, all of a sudden you're sweeping a rock, and it's even affecting it more. It's going 15 feet further.
That's because sweeping wasn't just removing the snow and ice, it was reducing the friction between the stone and ice. The rapid back and forth of the sweeping generates heat.
It all just comes down to this, yeah. It comes down to this. They're warming that ice up, maybe enough to generate a meltwater film.
A meltwater layer that reduces friction creates a literal path of least resistance for the stone to glide on more easily. Friction is reduced even further by another characteristic of curling ice: bumps.
All the other ice sports have a smooth Zamboni surface, effectively, and curling requires that the surface of the ice be roughened.
Spraying water does the trick.
And then when it lands on the ice, it freezes up and forms these nice pebble-shaped bumps. And if you look at it, it looks like an orange peel. That kind of roughness is about the right texture. That gives us the surface we need.
But wouldn't the bumps, like mini speed bumps, just slow the stone down? Actually, it's the reverse. The points reduce the total ice surface the stone rides on. The less surface contact, the less friction. And there's another reason.
If we're on smooth, frozen Zamboni ice in an arena, if that's making a nice seal with the bottom of the stone, you're going to eventually form a vacuum as the stone moves across the ice, and it really slows it down. You've got air pressure pushing on the stone, whereas if you can have it riding on a few points, then it's going to slide more smoothly, and you won't get any kind of a vacuum forming, and it'll go roughly twice as far.
The makeup of the stone itself plays a role.
Curling rocks are 42 pounds of granite, and actually the granite only comes from the island called the Lisa Craig that's off the coast of Scotland.
This type of granite is hydrophobic. It resists water. That means it will absorb very little of the meltwater layer at the surface. Absorption could reduce the lubrication, helping the stone glide toward the house. As the curling stone approaches the target, there's a good chance another team stone is in the way. When the stones collide, another wonder of physics takes place: momentum exchange.
When you see the collision of two curling stones, you're seeing the transfer of kinetic energy between them, and you're also seeing the transfer of momentum, the product of mass and velocity between them.
Well, there you have it, the basic physics of curling. From the hack to the house, from the coefficient of friction to the transfer of kinetic energy, curling is a sport that attracts the crowds and delivers excitement with a bump.
So if you take physics, we talk about that in a lot more detail, but we'll continue on here. Here we go. Come on. Okay, so we're going to push through here. Newton's second law. So Newton's second law, again, is F equals ma. So if we had in an ideal world, if we were in outer space and we dropped an elephant and a feather at the exact same time, they would hit at exactly the same time. Okay, we call this free fall. There's no resistance. The resistance we usually feel if we jumped off a building or dropped something is something called air resistance. But that doesn't exist in outer space. It's only found in a vacuum, and not like vacuum that you vacuum your house in. Actually, there is a slight vacuum created there. We can get into that later. But the idea is the vacuum of outer space. Okay, and there's a great little YouTube video on this. I told you, jumping back. This is an actual video from Apollo, an Apollo mission, and they drop a hammer and a feather at the same time on the moon. Here we go.
Both solar wind and penetrometer drum in the ETB.
Not quite yet. I haven't put the solar wind in yet, but I will shortly. I want to watch this. I have a good picture there. I've got
Beautiful picture, Dave.
Well, in my left hand I have a feather. In my right hand a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago, who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that?
So check that out.
Hopefully, they'll hit the ground at the same time.
Boom.
How about that? Mr. Galileo was correct.
So again, he proved that it was correct, that actually happens. Up to that point, people really didn't know if that would be true. And if you notice, the feather kind of falls a little bit slower than then the hammer just a tad bit, and that is because we are still on the moon, and the moon still has a little bit of air resistant type stuff happening on. Not much, but just a very slight amount. So this term, though, we talked about that it's going to accelerate due to gravity, but eventually every object's going to hit what's called a terminal velocity. Terminal velocity is actually where the forces become balanced. So, or zero again, but you're moving. Before we said if there was balanced forces, nothing was moving. Well, now I kind of lied to you. If things are moving and are balanced, they can be zero as well. So if you look, like when he first falls out, here's his first terminal velocity. When he pulls the parachute, he actually hits a new terminal velocity here right there. Okay, if you notice, the acceleration goes zero twice here. So here we go, he falls out right here, right there. Terminal velocity, acceleration is zero. Then he pulls the parachute. It slows him way down, but again, he hits a new terminal velocity. All right, so something as always people ask is if you drop a penny off like the Empire State Building, would it kill somebody? Okay, well, here we go. Let's let the Mythbusters tell you.
This myth originated in the Big Apple, atop an architectural icon, the Empire State Building.
The myth is that if you throw a penny off of a building this height, that it'll either get going so fast that it'll embed itself in the concrete at the base of the building, or it'll hit somebody in the head and kill them.
Adam and Jamie need to find out what is a penny's maximum speed when falling. In other words, its terminal velocity. Once they've done that, they'll shoot the coin at concrete, asphalt, and a head made from ballistics gel. It's time to see if Jamie's penny can achieve terminal velocity. The modified staple gun blasts the coin from 3 feet at the concrete block.
Look, you can see the penny imprint.
The penny traveled the 3 feet in 16/500ths of a second.
The rig has shown that we can fire this penny at about 65 miles an hour, which is at the upper level of what studies have shown that the terminal velocity of a penny would be.
So the test shows that a coin traveling at terminal velocity cannot penetrate concrete or asphalt. But what about flesh and bone? Remember, the penny myth talks about a penny shattering someone's skull. Enter Norma, Adam's ballistics dummy. Norma's cranium will take the full brunt of a penny traveling at terminal velocity.
Lights. Perfect hit. Lights off. Yep.
The penny broke through the thin layer of ballistics gel, but the skull is intact.
So, you ready to put that to the ultimate test? We've tried it on all the other stuff we've got. Want to try and catch it in your hand?
The penny is leaving an imprint in the concrete when it hits, so, I'm a little hesitant about catching it, actually.
The Mythbusters are about to find out what happens when a penny traveling at 64 miles per hour hits skin.
I'll do it.
Okay.
But you got to do it too, otherwise, you're like a wuss.
Okay, you first.
Okay. Still a wuss.
I'll kick your
Penny for your thoughts right about now, Adam.
I'm scared.
Okay. 3, 2, 1.
Ow! That didn't actually hurt that much.
Well, Jamie, take cover because Adam's taking aim.
All right. Firing. And 3, 2, 1. Well, that seemed to work like a charm.
Look at that imprint. You can clearly see where it hit.
The penny is shot from the slot at almost 3 times the speed of sound.
The high-speed camera result apparently is 3,000 feet per second.
Well, that's like a bullet. That's the speed of a bullet.
The coin still did not end up embedded in the block.
64 miles an hour just wasn't enough to cause any kind of damage to a person. And then when we made it go almost 3 times the speed of sound, it still wasn't enough to break the bones.
Yeah, I mean, the worst thing I can come up with is if you were looking straight up in the sky and you got hit in the eye, it probably wouldn't be very good for you. But even then, I don't know whether it'd take your eye out.
I think we busted the heck out of this one.
Myth busted.
Yeah.
So again, that is obviously a myth. Everybody always fears that, but it is definitely a myth. Okay. So again, if something's moving at that, we obviously have this thing called air resistance. That's the other thing, okay? The force that opposes the force of gravity, okay? So as you notice here, an elephant drops pretty much straight down, and then it says, a couple minutes later, 3 minutes later, now the feather finally hits. Air resistance has to do with the amount of air resistance, depends on the shape, the size, but also the speed. Okay, these you guys get. Bigger the shape, bigger the size, more air resistance. But speed, think about this. If you've ever stuck your arm out of the car when it's driving, when it's going slow, it's kind of fun. You get to mess around. You feel like you can feel the air and stuff. But if you're going like 70 miles an hour, you would not stick your arm out there because it would kind of like rip back and it wouldn't feel very good. Okay. This is from the Columbus Dispatch years ago. I'm sorry, it's from the USA Today. But notice, like, if at 10,000 feet we release a snowflake, it takes 75 minutes once the snowflake hits terminal velocity to reach the ground. That's why sometimes on radar in Ohio, when you guys are hoping for a snow day, you might look at the radar and go, look, it's supposed to be snowing. You look out the window and there's no snow. Okay. Or if you look out there and it looks like the snow has passed on radar, but it's still snowing, you're going, what's going on? Because it takes like another hour, hour and a half for the snow to reach the ground. On the other hand, raindrops only take about 8 minutes. Okay. If you've ever been out in a big storm and sometimes the big old storm comes and those big old raindrops can hurt. If you've ever been out in hail would even be less than this. It'd probably be around 2 minutes. It's kind of going, it can actually hurt. Skydivers, an average person, 150 pounds, jumps out. It takes them less than a minute to fall. So when people go skydiving, they only really get to fall for about a minute to 2 minutes, and then they have to pull their parachute to slow them down. Okay. The closest thing on Earth you can get to terminal velocity, at least here in Ohio, is to go up to Cedar Point and ride the power tower here. Okay. And what they do is they take you up there and they drop you. You used to be able to hold a penny there, and the penny would kind of lift off a little bit and stay with you. Okay. Or you can have some money and get on what they call the Vomit Comet. Well, what's that? Well, let's talk about that. These are our last two videos. I know it's been a little long, but I hope you've enjoyed it. Here we go.
I'm about to experience weightlessness for the first time.
Injection. And now you freeze.
Oh my god. Oh my god. That is so strange.
Oh my god. Oh my god.
This is totally freaky. This is way better than I expected. I'm just going to say this right now. I'm going up to the ceiling, and here we are. I am ridiculously excited because behind me is a zero-G plane. I'm in France. I was invited here by the YouTuber Bruce. This is Bruce, Diana, physics girl. We are flying some parabolas. We're going into zero-G. It's going to be awesome. Come on.
Welcome on board.
The principle behind weightlessness is pretty simple. The plane and everything inside it just need to accelerate towards the Earth at the same rate as a freely falling object in a vacuum. That is 9.8 meters per second squared. So you can think of your body as this pen and the plane as this bottle. And when it's freely falling, there's no contact force between the pen and the bottle, and so the pen feels weightless. So you might think the way to do this is just to put the plane into a dive. But that's not actually how it works. Instead, the plane starts climbing at a steadily increasing angle. With no windows inside, it's impossible to tell that this is happening, and all you feel is pressed into the floor with a force 1.8 times your body weight. This is because the plane's acceleration is directed upwards and perpendicular to the floor, and it makes standing very difficult. Not only are you nearly twice as heavy, all the blood drains from your head and into your feet, which made me pretty dizzy. So weak! Lying on your back is much more comfortable, and we're advised not to move our heads around and look straight ahead, because in hyperg, our vestibular system is hypersensitive to movement, which can lead to motion sickness, and that's why this is sometimes called the Vomit Comet.
I kind of like this.
It is fun. Feels like someone lying on you.
Yeah.
And I like that. Yeah. Once the plane is climbing at about 50 degrees, the engines are ramped down and the plane is put into a parabolic trajectory. It's at this point that you start experiencing weightlessness. I can feel myself getting lighter. Whoa, that is such a strange feeling. That is so weird. The plane and you are still moving upward, but you are accelerating downward.
There's Diana. She's the physics girl.
Then the plane peaks and starts speeding up again towards the Earth.
This is totally strange.
The whole time, the plane is accelerating toward Earth with the same acceleration as a free-falling object in vacuum. The pilots have to very skillfully adjust the thrust to perfectly balance air resistance and maintain exactly this acceleration.
Okay. Oh my goodness. How do you feel?
It's incredible.
So it's like throwing this bottle into the air. The pen inside experiences weightlessness from the time it leaves my hand until it comes into contact again. After 22 seconds of weightlessness, the pilots pull out of the dive, again subjecting us to hyper-G as the plane accelerates upwards. In total, we performed 13 of these zero-G parabolas, plus 1 Martian gravity and 2 moon gravity parabolas.
Okay, we are now in Mars gravity. In Mars gravity, I can do one-arm pull-ups, maybe.
Push-ups, wow. Push-ups like this. Yeah, like this. Wow. One out.
I am the Martian.
We brought along some experiments to do in zero-G.
So this is in about 1G of gravity. This is what the flame looks like on this barbecue lighter. Now we're going to try it in hyper-G, and then we'll try it in zero-G, and it should be...
We will see.
We take it for granted that flames have this distinctive shape, but that's only because of gravity. The products of combustion have more energy, and so move around faster and take up more space than the cooler air around them. Therefore, there's a buoyant force on them which is greater than their weight, and so hot air rises. This helps pull in the oxygen from around the flame to continue the reaction.
We're going through hyper-G. I keep blowing out the candle because the stress of hyper-G is significant.
In hyper-G, this effect is magnified, since the effective gravity is almost twice as much. This amplifies the difference between the weight of the hot air and the weight of the cooler air around it, and so the hot air rises faster, making a longer flame.
Oh my goodness. Look how that flame just wafts in zero-G because there's much less buoyant force to carry away. And so the combustion is not as good. You can see a lot of smoke coming off of that candle. That is incredible.
Hey, Doc.
Hey!
So we still have the gas flow, so this is why the flame is not circular.
It still goes up because
it is not a sphere, but it looks very strange.
In zero-G, the hot air is still less dense than the cooler air, but now there is no weight and no buoyant force, so the flame doesn't rise as high. This flame still maintains some of its shape because of the flow of fuel from the lighter. Otherwise, the flame would form a sphere, like on the space station, where it's very difficult to maintain the combustion reaction because it's hard for oxygen to access the fuel with all of the combustion products getting in the way. So if you're ever unsure about what the gravitational acceleration is where you are, well, looking at a flame is a pretty good way of finding out. I also brought along a slinky to try the slow-motion slinky drop, but in zero-G. Of course, here I couldn't dangle the slinky under its own weight, so I swung it around my head instead. The effect should be similar, with each coil stretched to provide the tension that keeps the length of slinky beyond that accelerating in uniform circular motion. I wanted to see what happens to the end of the slinky when I let go.
here we go. 3, 2, 1.
Did you catch that? The slinky remained fairly stretched out and kept rotating at about the same frequency as before. Initially, I thought this was a boring result, but then I realized the reason the slinky doesn't contract is because weight was never part of this equation. The slinky stretched out in the first place because it was rotating, and since it's rotating after I let go, roughly the same amount of tension is required to maintain that circular motion, and so it doesn't contract. In zero-G, it's possible to have a stretched slinky rotating in place without contracting. As long as the tension in the slinky provides the centripetal force, it'll keep spinning. This just goes against my intuition, which is made, of course, only out of experiences with gravity. Being weightless was an unforgettable experience, but maybe my favorite part was how it challenged my intuition. And that's the reason we need to do research in zero-G.
So hopefully you enjoyed that. One last thing, and we'll end on this. is our guy here. He talks about how how some of the astronauts had to do work in outer space. And this is how they trained.
Rather alarmingly, this aeroplane is known to its friends as the Vomit Comet. That's a clue to the way it flies. It doesn't just fly along in a straight line like a normal airliner. This is where astronauts come to learn what life is like without gravity. This is a proper astronaut training exercise. The way it works, it's quite complicated. The aeroplane flies a parabolic trajectory, which leaves you effectively weightless when you're inside it. But the easy way to think of it is that it goes over an extremely long humpback bridge. I'd also like to boast that at no point in my life have I ever been sick on an aeroplane, or in a car, or on a boat, or on a fairground ride, or any of those things. But that might be about to change. This little pocket has a bag in it, just in case.
Before the space race, no one was actually sure if human beings could survive in zero gravity. Some specialists thought our internal organs would just fall apart and we'd drop down dead. Or float away dead, anyway. So the Americans sent the whole menagerie of animals into orbit to see what it would do for them. And they all survived. That wasn't really the point. The point was... The point was... Oh, God. The point was, would a man be able to do something useful in zero gravity? For example, operate a spaceship. So what they did was they sent a trained chimpanzee called Ham into orbit on the 31st of January 1961. Ham had been trained to pull a series of levers in response to flashing lights.
The red lever for the red light and the white lever for the blue light.
If he did that right, he was rewarded with a banana-flavoured chip. If he got it wrong, he was electrocuted.
Ham is laced in his couch and wired for sound. The electrodes on his feet will give him a gentle shock in case he forgets.
Oh, it's a parlour. Sorry. Oh, hello. Hiya. How you doing? And this is where this child's game comes in, because it's a very, very similar thing. What happens is these lights go on in sequence. I have to get the same sequence when I press these two little buttons. If I get it wrong, it gives me a shock. Ow! And the chimp didn't have any problem with this. And he was doing it in 0G, which I'm going to try in a minute. I've forgotten. I hate this thing. Here we go. It was that one, wasn't it? Yes, it was. I can do it. Sorry. I can't do it.
So it goes on like that, but I hope you enjoyed this. I hope you learned a little bit. I hope you enjoyed the little movies. Until next time, Teamatron out.